what's that?
It's like we don't have tests or anything. The way people don't show up. It's like we don't have the test that's due on Friday and then another test next week. The test isn't next week, is that it's the next week?
Yeah.
Okay.
The Wednesday after Veterans Day.
Do we have school on Veterans Day?
No, we do not.
What day is Veterans Day?
Monday the 11th. Let me double check the calendar. Correct.
Monday the 11th?
Yep.
That's exciting.
Apparently it's also the birthday of the Sultan of Bataan. Whatever the hell that is, and why Google decided to tell me that is beyond me. It has like the Muslim holidays on my thing. It says the Prophet Muhammad's birthday is on November 9th. Why is my calendar doing that? I know classes are already started, but I'm just wondering where everyone is. 4 people, jeez.
Or it's like, probably not going to do the problem session after then.
Oh, we got 5.
Hi.
Yeah, we can do them. We can do the
Candy
problem
by
session.
chance?
I did for my first test, for my first class.
I'm going to say you have a child, I feel like you should have candy.
I'll wait for Peter to come back in. I didn't see you there, Michael, with your camouflaged.
Huh?
I couldn't see you. You're camouflaged.
Yeah, it was just a walk, like floating torso. Kind of weird.
Yeah, it was weird.
Break the laws of science, don't I?
That's
What
why
do you think you are, an electron? Just come in and from any door?
I disappeared. Well, I mean, I couldn't see him. He's wearing camo pants.
Me and Pierre saw your wife last night.
Oh, yeah?
We're in that study room in the other building, studying for physics, and we tried to recruit her. She didn't want to do physics with us. I tried asking her if she had a cheat sheet for physics, like she does for her astronomy class. She goes, no. We tried though.
I mean, like, we just kind of do our own subjects. I mean,
Do you want to come do physics with us? She goes, I got a class to teach. She dug out. She left us hanging.
later, losers. Alright, just so you guys know, I'm feeling kind of sick. I'm a little much improved. I've got some sort of stomach thing. I didn't know if I was going
Did
to
you
make
get
it.
your flu shot?
Yeah, I did.
Did you get sick after your flu shot?
I did have a reaction to it, but it wasn't bad. I had my arm was sore where they stuck the needle in.
I do not have a flu shot.
You gotta man up.
Ever.
I like getting shots.
Those are
Yeah.
so bad for you.
The shots, no, they're fine. The vaccinations are fine.
I had one. They usually don't hurt me. But when I was pregnant, they gave me that, what's that,
Oh, yes,
3
yeah.
tetanus shot one?
Tdap.
Yeah, that one was sore.
Yeah, that hurts.
That one, I've never been sore from a shot in my life. They gave me that one, I felt like my arm was
You look like
broken.
that big and it's screwed all the way.
Tdap's for you all, just tetanus in general.
Horrible. And they gave it to my baby when he was born. I felt bad for him. But it was one of those better him than me things, even though he was a newborn.
Hey, it beats good in the whooping cough. Let's protest this or whatever. Alright, well, I guess, where did Peter go?
No.
Anyways, I'm just wondering when people are going to show up. That's why I'm just kind of dragging my feet. So, since I'm not feeling well, I'm just going to kind of stay behind the desk so I don't get you guys sick.
Even with without vomit?
I don't know.
Well, I was observing what's his name, Jeff Tibbetts' class, and I had to leave to go throw up.
Ooh.
Ooh,
What? I missed that.
Oof.
you had to leave class to go
Kinda
puke.
guessed it, didn't I?
Is cesium hydroxide a solid, liquid, or gas?
What, like, at this temperature and pressure, it's a solid.
I'm thinking basic chem.
Did you take the radio?
No,
I
I
Everybody takes it already?
Yeah.
Did
Wait,
you take
how
it?
many times can you take it?
What kind of question is that?
Take
I
one.
thought we
How many
had
times?
until November
Which
1st
test?
to take
Wait,
it.
Go Friday.
chemistry test.
The retake? Yeah, once, yeah.
Once?
What, you mean the one in the testing center?
Yes.
Yeah, once.
I was thinking.
I don't know how you got to that.
I'm probably taking it tomorrow or on Friday on the day of. Or is that? Can you not take it on the
You
day
can take it Friday.
Friday at 4. They close so early. I don't get why the TLC closes so early.
It was
I'm
Friday. They
pretty
wanna
sure
go
they
out
don't
and hit
close
the
at
bar.
No, every day it's like 4:30.
No, they're open
Isn't
until
it?
6 on Saturdays and Fridays. I'm pretty sure
They're not open on
until 6.
weekends.
Yes, they are.
No.
Girl,
Library
I
ain't
take
even
my
open on
test
weekends.
in the learning center.
They don't
They're
offer
open
testing, though.
Saturday.
No,
We gotta look this up.
Are you gonna go out for Halloween?
Hell
I'm
no.
working.
Okay. So, that was just one
I
thing.
am. My baby's gonna be a dump truck. We're gonna go trick or treating.
Yo, I saw this costume today. I was working at the Y and they had like these kids come around costumes. This kid had like a full dump truck
We
like
don't
thing.
have
He
him.
put candy in his like front thing and he pulled these strings and it went into his
He's
back.
gonna be a dump truck.
Cool.
He's gonna be a dump truck.
Aw.
No, yeah.
One thing that scares me is what if kids are like behind him and just like steal his candy?
Yeah.
My
See
baby?
that?
I kicked him out of his ass. I mean.
All right. Well, I guess this is what we're gonna get. So I'm
More of
gonna.
a trick than a treat.
Being with you guys is always a treat. All right. So we're talking about quantum mechanics, and so here's some wave-like behaviors. So if you have two waves in phase, they constructively interfere. So if they have the same where the amplitudes and troughs are, trough is the bottom part, the peak and the trough. If they are aligned, then the waves grow. If they are misaligned, if you see the bottom one here, where there's a peak, there's a trough, and vice versa, then they destructively interfere and go away. So that's a wave-like behavior. There's also comparing a wave and a particle. So imagine you have a series of ocean waves, like on the top picture, headed towards like a break wall with a hole in the break wall. Then the waves will diffract in that pattern shown there. And if you instead of a wave, you compare this to particles. So imagine, say you got a guy here with a machine gun and is shooting a bunch of bullets at a wall. There's a hole in the wall. Basically, the wall will block all the bullets except for where there's a hole in the wall and the bullets go through. If bullets offend you, think of someone hitting golf balls then or throwing baseballs or something of the sort. So that's particle-like behavior. And let's compare this to, let's show wave-like behavior with two slits. So if you have a light source, and the light is going towards two holes, this is known as a two-slit experiment. What happens is the waves are kind of going towards the wall, and then they diffract out. And as they diffract, then they interfere with it, constructively and destructively interfere with each other. And what ends up happening is there's in the middle, depends of course where you position things. There's a lot of times there's a kind of a peak in the middle, and then nothing, then a smaller peak, and then nothing, and then like a humps kind of like this. So that's the pattern that you see when you have a light shined at two slits. So two slit experiments. And so light also, light likes to act like a wave. So what's weird about light is if you expect it to act like a wave, it'll act like a wave. Then if you want it to act like a particle, sometimes light will act like a particle. Light usually acts like a wave though, to be perfectly honest with you. And this is what Einstein got his Nobel Prize in. was the photoelectric effect. A lot of people think it was due to relativity, but Einstein actually, in Europe, people hated Einstein. He was very unpopular.
You told us.
Yeah.
I remember this.
Yeah. The Germans said he was Jewish.
Something I didn't know
English,
before.
yep. English said he was German. So they hated him. But they loved him. They loved him in America, and we still love him in America. It's part of our pop culture, actually.
My Indian teacher at Meyerson said he has his pictures all on his wall.
You're Indian, like. Okay.
Dr. Booty.
Oh, Booty. Oh, okay. I was thinking like, oh, yeah.
No.
Dr.
We're pointing out
Yeah.
Germans and I pointed out his race too.
Yeah, Booty's. I like Booty. He's insane.
His son,
He likes to party.
he was, our testing, he was like, oh, let's get a short test, but no, we were in there for 2 hours.
I'm sure it was easy for him.
He came around after laughing at us. You guys have been writing for 2 hours. It's crazy.
Okay, so photoelectric effect. Well, let me explain what it is. So imagine I'm holding a basketball in my hands, and I say, all right, knock the basketball out of my hands. And if you like slap it, I'm like, ha ha, you can't do it. Then you punch it, I'm like, ha ha, still strong. Then you take like a sledgehammer, and then whoo, you can knock the basketball out of my hand, right? So what is the energy of the basketball? The energy of the basketball is the energy of the swing of your sledgehammer minus how strongly I was holding on to it, right? That's how much energy is left over from the basketball bouncing around. So the idea, instead of a basketball, think of an electron stuck to a surface of a metal, and the kinetic energy, the energy of the electron, is equal to the energy of the photon. So the push of the sledgehammer for the basketball, and then how bound the electron was. So this is, like I said, what Einstein got his Nobel Prize for. And it observed something. If you had a metal surface, and then it's always ultraviolet light, but if you shine ultraviolet light on the surface, I mean, we can't see ultraviolet light, but I'm mimicking it with colors. Here's red with low energy, yellow with higher energy, green. Suddenly, with high enough energy, electrons start being ejected from the surface. And the electrons all have the same kinetic energy for a specific color or wavelength. If you increase the energy, so decrease the wavelength, increase the frequency, you get electrons coming off at higher kinetic energy. And if you increase the intensity of the light, you get more electrons. So the fact that lower energy photons cannot eject electrons, this is one of the reasons why cell phones can't cause cancer, because microwaves can't ionize things. So it doesn't matter how many microwaves you have, it's not going to ionize anything.
You said you increase the light, and what happens?
If electrons come off, you increase the intensity, more electrons come off. I tried to show this here with the blue light, and you had electrons coming off, and then if you increase I just said a thicker arrow, there's more electrons coming off, which I showed with my picture. And this was a big deal at the time, so we didn't quite understand. So kind of like how atoms are the ultimate particle of an element, the photon is the ultimate particle of light. And they have little tiny packets of existence, and the energy of a photon is equal to h, Planck's constant, times nu, the frequency. H is 6.626 times 10 to the minus 34 joules times seconds. This can also be, because wavelength times frequency is speed of light, it can also be hc over lambda for energy. Have you guys seen Stranger Things Season 3?
Yes.
Remember, Planck's constant was the code.
The code, yes.
Yep.
Yes.
Season 3 already?
A long time ago.
Yep, so...
That's like the first time you referenced a show that I know.
You guys say I watch too much TV, and that's what you know. Okay, so let's apply this. A nitrogen laser pulse has a wavelength of 337 nanometers and contains 3.83 millijoules of energy.
Planck's constant.
So before I do that, let's say I have $20, and
No, I wanted
how many $1 candy bars can I buy? So if I have $20, how many $1 candy bars can I buy?
20, and I can keep the $20 bill.
Oh, really? This is. It's like, I feel like I'm losing in this negotiation. I mean, of course, the answer is your principal over your cost per item, right? That's how I figure this out. The principal, that's the amount of capital that I have, divided by the cost per item tells me how many things I can buy. Okay, so how many photons I have, so the same idea. Instead of the principal, think of it then as the total energy over the energy per photon. So just like when I buy something, the principal over the cost per item, I have the total energy instead of the principal, and I have the energy per photon instead of the cost per item. So the energy per photon is h nu equals hc over our wavelength, and our total energy is 3.83 times 10 to the minus 3 joules all over h, so 6.626 times 10 to the minus 34 joules times second times speed of light, 3 times 10 to the 8th meters per second, all over the wavelength, 337 times 10 to the minus 9 meters. If you look at the units, joules cancel, seconds cancel here, meters cancel there. So just left with nothing, no units, so it's just a number. What is it? I'm just gonna look in that. Here we go. Sneaking and looking into the book
You have to convert nanometers to meters.
to 10 to the minus 9. So nano is 10 to the minus 9. Kind of like milli, 10 to the minus 3. Okay, if you put that in, you,
Nano and milli, micro?
yeah. After that is pico, then femto, then atto.
You just have those all memorized, don't you?
Not all of them.
Just the first.
Well, I usually use the ones that I've had to use. I've done more short scale than large. Talk to my wife; she can tell you all about the large scales. Things like
I know.
stars, holes. So this is 6.49 times 10 to the 15, and then photons. So what does that tell you? That's a big number.
Massive.
It's a large number. So photons are tiny, just like atoms. So how are you doing? Questions with this? All right, why don't you try this one out? And I'm not going to go around and talk to you guys. I'm afraid to get you guys sick.
Yeah, no, you can stay there. I'm joking.
But no, it's it.
Joking.
Hey,
You know you're not feeling
spread,
good, you never sit down.
spread the aloha, not the germs. So why don't you try this out, and I'll try and guide you. Laser pulse at 532 nanometers has a pulse of 4.67 millijoules. How many photons is this?
Can you scroll up real quick so I can copy the equation again?
Is that one there?
Get my wavelength. And I am going to add that.
So did you like Stranger Things season 3?
I did. I'm obsessed. I was a little bummed that they killed the brother at the ending.
Well, there was a redemption for him of sorts.
And Hobbs died. Was that his name, Hobbs?
The not.
No, was it?
Yeah, you're talking about the police chief.
Yeah.
Question, yeah.
What is that second parentheses? How do you get that number?
3 times 78.
Yeah.
That's the speed of light.
Oh,
I'll be playing the speed of light in there. What is this equation?
That should be fine. I'm sorry, 530.
And the lambda is Planck's constant.
Lambda is wavelength.
So I'm taking my total energy, which is the pulse, of 4.67, and I'm going to divide them by this constant.
You guys see how to do that? Trying to put your calculator.
So that's just the energy per photon that you had to divide that 532 by it.
This right here is the energy per photon. That's HC over lambda. This is energy divided by HC over lambda.
First pulse is the lambda. Okay.
So hopefully you guys are getting answer B. Just put in my calculator. You're not getting it?
Now I have to re-enter it because it won't let me do a fraction in my denominator, so I got
No.
What you can do,
No,
you can do this as a you can do this term as a
You're
multiplication.
using the 10 to
Yeah.
the minus, or you're using the times 10 by.
Yeah, I got put them. Just taking the action.
That's just
out.
a.
Weird.
Because you're divided by a divider, you're divided by a fraction, so the fraction
You can
becomes
put a
multiplication.
fraction into a fraction.
No.
Yeah, you can put a
Alright.
fraction in the numerator or denominator, so you just.
Just make sure you put a parentheses around it if you do that.
Yeah, that's like what he did is exactly.
Well, here, maybe this will help. Oh, stupid calculator.
What was it, 4.67?
But then you gotta turn it into joules.
Yeah, times 10 to the negative third. And now you put the 3.7 times 10 to the negative 19 on top. Okay, so it's not
You guys follow? Okay, you guys got it. Okay. All right. Any other questions with this, or?
hang on 1 second.
It's 2.5 times 10 to the 16. Oh wait, it shouldn't be B. I'm sorry, it should be A.
Ooh, that makes me feel real good. I'm
I'm
on cloud 9 right now because I did not get that answer.
I'm sorry, I wasn't. I picked
No,
the wrong one.
it's totally fine. It just makes me feel good that I'm getting it. Cool.
So what's the units for,
Just-
just joules?
Just photons.
Photons.
Just stuff.
Okay.
No units in terms of dimensionality. Just number. Yeah.
Life-changing.
Okay, so let's talk about the wave-like nature of matter. So, matter actually has some wave-like properties. And we're not going to go over the proof for this. This is really high-level physics. And the wavelength, this is known as the Broglie wavelength. It's Planck's constant over the momentum, which is mass times velocity. So that is a wave-like property. It's the Planck's constant over momentum. And so what is the wavelength of an electron traveling at 2.65 times 10 to the 6 meters per second? So you just straight plug and shrug this equation. So this is, well, I'll do this over here. Lambda D is
Oh, I thought that was
Planck's
an O.
constant. What, it was what?
I thought that was an O.
O? That's a D.
It was like a Latin knot, yeah.
Is it
D like Dracula.
why is it capital? Should it be,
I don't know.
is it technically supposed to be capitalized?
Yeah,
Okay. And what is the D stand
de Broglie.
Royally, what?
That's
Oh,
Broglie
the
wavelength.
Broglie.
Yeah.
Gotcha.
The
We would
Broglie.
probably-
Oh my gosh.
something like the broccoli.
Okay.
Broglie. That's at least how we always pronounced it. Okay, so H is always 6.626 times 10 to the minus 34 joule seconds. Oh, and mass, this is the mass of electron.
Just looking for
It
where to get the
is
height.
it's 9.11 times 10 to the minus 31 kilograms. That's the mass of an electron, and the velocity is given 2.65 times 10 to the 6 meters per second. So let's look at the units. We
Not
have-
volume.
velocity?
I did.
What's that?
Give it on the side.
Oh, up there.
I thought it said volume at first.
Then we're not looking for velocity.
We're looking for wavelength. Okay, so a joule is a Newton meter. So a joule then is a kilogram meters squared per second squared times second all over kilogram meters per second. So unit-wise, purple. This second goes away. These 1/over seconds go away. Kilograms go away, and meters go away, and we're left with meters as far as the units.
So should the
Length
question
is
say
in
what is the
meters.
wavelength of a?
Yes.
It says calculate the wavelength.
Oh,
Yeah.
that one. what is the question?
Up top, we're up top, Peter. We work under the problem, not above the problem.
Okay. So if you carry out the calculation, it's 2.74 times 10 to the minus 10 meters. And that's really small. Well, it's about half the size of a hydrogen atom. So a hydrogen atom is about 5 times 10 to the minus 10 meters. So it's on the atomic scale it works. But for us, so imagine instead of 9.11 times 10 to the minus 31 kilograms, what if you put your about 118 kilograms, you put 118 kilograms mic there instead. So that's going to be 33 times, 10 to the 33 times larger. So that means my de Broglie wavelength, even if I'm traveling that fast, is going to be something on 10 to the minus 43 meters. So I mean, my wavelength, my wave properties are pretty much non-existent. So I'm not going
You
to,
don't exist.
as a wave, you're not going to pull a Cartesian philosophy on me, are you?
No.
So I think, therefore I am. Okay, so let's see if we can do the opposite. What is the velocity of an electron with the de Broglie wavelength being 1.2 times 10 to the minus 10 meters? And mass of the electron is that. Let's see if you can do
The mass of the electron is 9.11.
11 times 10 to the minus 31.
Is that always a thing or no?
That's the mass of an electron at rest. So,
So for right now, all we need to know is that's the mass of an electron.
yeah,
So when it asks you to calculate this using the mass of an electron times
velocity.
the velocity, it's always going to be those two.
For this class, thing is that
Perfect. That's all I need to know.
you
All I
can
need
get
to know for this
you can
class.
get things going relativistically, and it's kind of, we don't entirely know. So when things start moving faster, their momentum increases. Some people say their mass increases, but I mean they're apparent. Momentum increases. You could argue it's their inertia as well. It's one of those.
Got it.
It depends. Anyways, yeah, lambda d is h over mv, which implies v equals h over m lambda d equals 6.626 times 10 to the minus 34 times second, all over mass 9.11 times 10 to the minus 31 kilograms times the Broglie wavelength 1.2 times 10 to the minus 10 meters. If you put this in your calculator, you get 6.1 times 10 to the 6. Is that what you got?
Yeah. Well, it's 6.0 by hand. It's 6.1, yeah.
You guys good? Or questions? I know I'm not going around and bugging you guys because I'm trying to
There's
quarantine
only
myself.
6 of us here.
Yeah.
Need to have a fair room.
So you're trying to, so that,
Always been a talent of mine.
No.
Question?
you're trying to get it to joules. I'm looking at the book.
You're trying to get
The top one, the one that we first did, not this one. That
Okay,
one.
this one.
For the joules per, you want it in joules, yeah? Or,
The wavelengths and meters.
yeah, I'm trying to figure out this kilograms times meters squared over second squared times
Kilograms
second.
times meters is joules.
No. A joule is a Newton meter, and a Newton is it's mass times acceleration. So displacement over time squared is acceleration. So mass times
So it's
acceleration.
mass, not meters.
Which one?
The m squared over s squared, the m stands for
joule.
mass.
So like 1 joule is a kilogram meter squared divided by a second squared.
Okay. So
That's
it's
the
meter.
dimensionality of a joule.
Okay.
So if you have the units being joules times second divided by kilogram times meter per second, that's the dimensionality of it. And a joule is a kilogram meters squared over second squared. The kilograms cancel here. See that?
Uh-huh.
This second cancels with this squared. This meter cancels with this meter squared, and then 1 over seconds cancels with 1 over seconds. So
Okay.
you're left with meter.
Oh yeah. You're left with 1 meter. Your meters can. Okay.
Yeah.
Perfect.
Your meter is the only unit left over.
That's the problem I needed solved. Thank you.
Other questions? Okay. All right. So next thing I'll talk about is the uncertainty principle, and where this comes from is linear algebra, actually, and it's Heisenberg's uncertainty principle, and his uncertainty principle says the uncertainty in x, the displacement, and the uncertainty in p, momentum, is greater than or equal to 4 or h over 4 pi. And sometimes you can see it is written as h bar over 2, and this h bar is h over 2 pi. So h being Planck's constant and pi being the circumference divided by the diameter, a rational number. So okay, so with quantum mechanics has 7 dimensions. So meaning you have a point, and we have 3 dimensions that describe where this point is. So the x, y, z defines the point. Now you have this point. This point is different if it's going in this direction versus this direction versus this direction. So you have 3 dimensions that describe where things are going. So x, y, z, the direction, x, y, z, the position. So this is saying that you only know so well where something is and where something is going to a certain degree. Oh, and I guess, can anyone guess what the 7th dimension is in quantum mechanics?
Time.
You got it. Yeah. So position and momentum, and but there's uncertainty, so you don't know both at the same time. Meaning,
Which
if
is why
you
we're gonna time travel one day.
you can a little bit, not so much. You can get
Find
weird
the
things.
black holes with Professor Jen.
You can go forward in time, backwards in time. You can do it on a small scale.
Can't you look back into time based on the speed of light from the other planets? Like when
Well,
you
yeah,
when you get back, you're technically looking back in time.
Because it takes that long.
Yeah. I mean, like when you're looking at the sun, the light takes 8 minutes to get there. So you're looking at the sun 8 minutes back in time, right? And then look at a galaxy, then it becomes billions of years.
Relative to us.
So
Time travel one day.
You already are.
Find black holes.
so which means if you know where something is, you know the position very well, you have no idea what the momentum is, where it's going. And the same, also, if you know the momentum very well, you have no idea what the position of something is. And with this, though, it's not so much you even know where it is, it actually occupies all that at the same time. So like electrons, when you have them in particle accelerators, so if you know the momentum very, very well, so like if you have it, like you have electrons zooming around a particle accelerator, what happens is you very heavily define the momentum, and then the position becomes very uncertain, and the electrons become like really thin, sort of pancake-like, like long, thin pancakes. And the question is, so if the electron stretches out to this long, thin pancake, is the electron, where is the electron? It's actually in all these positions at the same time. So it occupies more than one spot at the same time. So it's not with this. I mean, we're so used to classical mechanics being like gravity and that kind of stuff that you're studying in 170. I mean, I think it's okay that this is, here's my position, here's my momentum for this thing. But for an electron, it's in many different places and can also have different momentums as well. So it's easier for me, at least conceptually wise, to understand the position better than the momentum.
Is it that it's just in so many different places at once, or is it just because you can't split time up?
It's because it's in many different places at once. The electrons can be in 2 different places at once.
So it's not like frame rate or something.
I don't know what that is.
Like if you have a low frame rate and something will look like it's.
Oh, I see what you're saying. Yeah.
Exposed, right?
Yeah. No. It's not. It's something like that. Because it's really the material, the electron, or what it's. We usually talk about electrons, though. I mean, you can have something else like a muon. Muon is like an electron, but it's about 1,000 times as massive. It's in many different places at once. It's not just dancing around. It occupies a large area. Well, relative to and then like a nucleus, right? So like electron cloud's pretty big relative to a nucleus. That make sense or not make less sense? Because this is confusing. I think quantum mechanics is fairly confusing.
I didn't know anything confused you.
Oh, lots of things confuse me. I just know freshman chemistry very well. So here's a classical trajectory. So imagine you're shooting a gun, or if guns offend you, say you're shooting a basketball, or you're throwing a basketball, and what happens, it's just pew, like a parabola. But since if you shoot something like an electron, and then say it does behave in gravitational field or something like that, you would get uncertainty with where the position and actually momentum is, where it's going. So there is actually a range, and the question, like if you were to look at the electron in like a slice in one of these, the question is, where's the electron? Well, it's actually in all those places at once. So it's not like it's just in one spot moving around. It actually occupies like a big space.
So is it doing this all the time?
Yeah.
So I'm here and in Australia at the same time.
You're not an electron. Electrons, though, yeah. But the thing is that the probability, the longer the distance goes, the probability goes down. I mean, anything like if you a centimeter away is about the same probability of being like a Jupiter.
So if you know the exact position, then you don't know how fast it's going, where it's going. Is that what it says?
Yeah, if you know well, even more confusing, if you know the exact location to like 100% accuracy, then your uncertainty in your momentum is infinite. Then it would be going everywhere at the same time.
Okay. So,
That's some black magic stuff.
but at that point in time, you know where exactly it is.
Yeah, I mean, which means that if you know exactly where this is, you have no idea which direction it's going.
Right.
So I mean, it would really, the probability would be a sphere where it's going next. And
Yeah, I guess that makes sense. It's just like a slice of this period of time.
Yeah.
So.
yeah, but the point is that it's very rare that you know exactly what the position is. So it's typically
So it's always like a little ratio of the two?
yes.
Okay.
Yes. By this ratio, the uncertainty of position times the uncertainty in the momentum is greater than or equal to Planck's constant over 4 pi.
I'm just thinking 4 pi is, no, you need 4 pi r to be surface area, right? So it
No, yeah, it's not.
So
It's
it's not described like a shape or anything? Or is that for
this proof is from linear algebra, and it's the mathematical proof. So it's not necessarily based off of geometry. It's more based on matrix algebra.
Right, okay.
So there's some really weird things. I don't remember all the proof, but like e to the pi I is equal to -1. So
Oh,
pi is not
Euler's
always, what's that?
Euler's or
Yeah, Euler's number. Euler, whatever.
It's just going
Oh, you there?
Euler or whatever. I mean, pi is not necessarily confined to circles.
Yeah.
So
It's just a ratio.
no, pi is another weird number. I mean, yes, a circle's circumference divided by the diameter is pi. That's true, but pi is not, as far as the number is concerned, is not limited to geometry. It has other. It's found in other places,
But like
Never seen it anywhere else.
like right here. I mean, e to the pi I is equal to -1. That's another. I mean, because there's a bunch of other things. It's found in many probabilities, and other like so.
I've heard like E being used in a bunch of different places. Like statistics and stuff.
Yeah. But as you can see, E and pi are actually related.
Right.
By that equation. So this is, I mean, just this is above and beyond the scope of this course. You're talking about graduate level mathematics right now.
Wait, that doesn't relate to what we're doing right now.
Not at all.
Sorry.
Peter's just asking.
Peter likes to go really high into his math.
Peter is wondering where the Heisenberg uncertainty principle comes from. And this has to do, the proof of this is in matrix algebra. So,
Sorry.
I'm too tired not to argue back. I'm just
It's exam week. We're all delusional.
I'm just playing along, answering the questions. That's one thing. If you ask me a question, I will give you the answer, even if it's super freaking complicated. Okay, so this is Schrodinger's wave equation. Sorry, we keep on. Okay, so here is Schrodinger's wave equation. Schrodinger's wave equation is H psi equals E psi. So H is known as the Hamiltonian operator, and E are the energy levels. Psi, that looks like a pitchfork. That's known as the wave function. And so H psi, so the Hamiltonian operator, what is an example of an operator? Like these are operators right here. Plus, minus, multiplication, division. So addition, subtraction, multiplication, division. So if you have 2 plus 1, you say, oh, the number 2 is then having the addition operation on the number 1. And then 2 plus operated on 1 equals the number 3. So that is an example of an operator. So you have this operator on the wave function and out splits the energy levels. And the energy levels, these are discrete, meaning they're exact. They're not continuous. So think of it like a floors in an elevator. So when you take an elevator, you stop at unit floors. You can't really stop in between them. So same thing with energy levels for electrons. They don't have in-between states. Actually, they do, or they can. Anyways, later on we'll talk about orbital shapes, and this is what the orbital shapes are. So you have the wave function, vector dotted with its complex conjugate. A complex conjugate is like if you have a complex number, it's like 2 plus 3i. The complex conjugate would be 2 minus 3i. So it's just you have the
So
or one is plus, one is minus.
Side to the what?
Psi star. Psi dot psi star.
We're right into that math that doesn't even look like math.
And then
D tau, that's all space. So you integrate. This is not on the next test. I'm telling you where this is from. so I shouldn't get into a long discussion. We'll talk about that later. That's where the orbital shapes come from. It's that. You integrate over all space with the wave function vector data with its complex conjugate. So let's forget all the crazy math, and we've solved this for the hydrogen atom, and the e to the n, so the n is the energy level number. We'll talk about n in a second. Is equal to minus 2.18 times 10 to the minus 18 joules times 1 over n squared. N being n equals 1, 2, 3, and so on. And also this number here, this is also referred to as the Rydberg constant, and it has the symbol R infinity. So things for electrons, a free electron has 0 potential energy. So just like in enthalpy, remember in last class we talked about standard states, we set the enthalpy of elements to be 0. The 0 for electrons is a free electron at rest, so meaning it's not moving. And then a bound electron has negative potential energy. So if you're wondering what negative energy is, it's just relative to a free electron. And okay, so this is something that's gonna, as I go through this, it's gonna sound really weird, but eventually it'll make sense, or I hope it does. So these are the quantum numbers. The first one, n, we talked about it up here with this e to the n. N is the principal quantum number. And n, the little epsilon, that means exists. N exists as positive whole numbers. 1, 2, 3, 4, 5, on up into infinity. So whole numbers only. So it can't be 1.5, it can't be 1.75, it can only be 1, 2, 3, and so on, whole numbers. So this is known as discrete mathematics, meaning only numbers, not fractions. And L is the angular momentum quantum number. L exists from 0. N cannot be 0, but L can be 0 up integer steps up into n minus 1. And if you've heard this before, when L is 0, that's an s orbital. When L is 1, that's a p orbital. When L is 2, it's a d orbital. When L is 3, that's an f orbital. If you must know, S stands for sharp, P stands for principal, D is diffuse, and F is fine. Those are spectroscopy terms. No one typically uses that. Some people think S means spherical and P means perpendicular, but they don't.
Does it mean static?
No, it means sharp. It doesn't mean static. Sharp. Because the lines, when you get the lines, they're very sharp.
Is that n minus 1 or n to the negative?
N minus 1. And then the next quantum number is the magnetic quantum number, m sub L. And m sub L exists from minus L integer steps through 0 to plus L. And then, not in this chapter, but it's the next chapter, but then the spin is the last quantum number. And for an electron, it's either plus 1/2 or minus 1/2. So, which means that an electron is a fermion. So what is a fermion? Fermions are particles that have spins that are fractions of 2 integers that are not integers themselves. Meaning like 4 over 2 is a fraction, but that also equals 2. So 1/2 is a fraction of 2 integers that's not an integer itself. And boson, so a photon is a boson. Photons have a spin of 1. So what is a spin? So it's easiest to think of it as like when electrons in the s orbital. It's a sphere. It's a spherical shape. And at any given time, the entire magnetic field of the electron points in a certain direction. If it's more than slightly above absolute 0, it's going to move around. So that's a spin. And if you have 2 electrons, they're going to have the same thing but oriented in the other way. So that's a plus 1/2, minus 1/2, meaning you can fit 2 electrons in a spin.
I'm recording now, sorry.
Okay, it's being recorded there too.
I'm on my phone way more than I'm on that. It's just
Okay, all right. Okay. And then Pauli exclusion principle. This is also next chapter, but I don't talk about it now. Pauli exclusion principle, no 2 fermions may have the same set of quantum numbers in the same atom. So this is the reason why matter has structure. So if I if I try to come up towards the screen and put my hand through the screen, what happens is, maybe it's easier with the desk. If I try to put my hand through the desk, the desk fights back. Why does the desk fight back? Because the electrons in my hand are trying to occupy the same space as the electrons in the desk, and what happens is they push back. They're also negatively charged, but they push back. And that is what gives matter structure. Energy, light is energy, or a form of energy. Energy has no structure. So you can put as much energy in the same space as you want. There's no limit to it. So to give you an example, when I was in grad school, the laser, I guess a postdoc too, I was working with lasers that had pulse lengths of about 15 picoseconds. So the energy, or I should say, no, the power of the laser was about 2 gigawatts. And if you look at Oahu, the amount of electricity that Oahu generates is about 1 gigawatt. So Maui is about 300 megawatts. So let's see here. That would be about 7 times. So the laser I worked with, if you took 7 times the amount of energy output of the island of Maui, that was about the energy that each of the pulses. It was 20 times a second. So 20 pulses a second. Each of those pulses had 7 times the energy output of Maui. So how is it possible you can fit so much energy in a really small space? It's because bosons can occupy the same space at the same time, whereas electrons, which are fermions, cannot. And it's the electrons are what give matter structure. So interesting. I always like this. I think it's kind of cool. All right, so here are the quantum numbers. Let's talk about this then. What are the quantum numbers and names for the orbitals in the n equals 4 principal quantum shell?
Let's see.
So if n equals 4, we have n equals
It's
4.
in the
That
N,
means,
the principal.
yes, L can be 0, 1, 2, 3, or 4. Oh, I'm sorry, not 4. It can be 3. Sorry. So because L, yeah,
Zero. It's n minus
because
1,
L
yeah.
exists from 0 to n minus 1.
And n equals 4.
So
it's one.
then m sub L here has to be 0 because m sub L exists from minus L to L. So if L is 0, m sub L has to be 0. If L is 1, m sub L can be minus 1, 0, or 1. If if L is 2, m sub L can be minus 2, minus 1, 0, 1, and 2. If L is 3, m sub L can be minus 3, minus 2, minus 1, 0, 1, 2, 3. So, and then you count them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
Is it always going to be as easy as just squaring whatever n
Yes.
equals?
Yeah.
You always just square it. So if they give you n equals 6 and they're asking for how
That'd
many
be 36.
orbitals, 36.
Yeah. And
Just should have led with that.
that was my next point.
Oh, okay. Sorry.
And
I'm on it today.
and the number of electrons, it's 2n squared, because the one could be spin up, spin down. And then the orbital type, this is an S, this is a P, this is 4S, 4P, 4D, and 4F.
How do we find those again? Can you go back to
Which one?
there was a little section on this page before. The L0.
L0 means S orbital, L1 is P orbital, L2 is D, L3 is F. I barely eat anything in a day.
Oh, I'm eating nothing but candy.
Yeah, Peter had the biggest burgers for lunch with some fries.
I had some rice.
I
I
had
had
the
rice and
chicken.
ginger ale.
It was really good, but it wasn't enough food for $12.
So
You could,
yeah, so go back to the orbital type?
You go by the L. When L is 0, that's an S.
L is
When L is 0, that's an S, and N is 4, so that's 4S. When N is 4 and L is 1, that's 4P. N is 4, L is 2, that's 4D. N is 4, L is 3, that's 4F.
What if N was like 5? Then
What's L?
L would go up to 4.
Yeah.
So that would be
We call that G orbital. We only really.
and an orbital is what exactly?
It is the place that the electron can occupy itself.
So is it like the
Yeah.
like the
Orbit.
I'm using it right, like a valence shell?
Yeah, that's exactly what it is.
Where? So which level of
That's the Bohr model when he said the orbits, but the Bohr model is wrong. But
Proven it.
they use the word orbital because of Bohr.
okay. So it's just where the electron is
Yeah.
on
There's
the
no more
atom.
shells, it's a cloud now.
Yeah. I'll show you pictures, not this class, but next class. Okay. And so what? Why do we care? Periodic table. This one here are the s orbitals. Here are the p's. There's 6 or 3 orbitals. So, because each orbital can hold 2 electrons, so these are the s. This is 1s, 2s, 3s, 4s, 5s, 6s, 7s. And 2p, 3p, 4p, 5p, 6p, 7p. These are the d's, and these are the f's. So the quantum mechanical model is the reason why we have a periodic table the way we do.
Are we gonna be, do we need to memorize this?
No.
Okay.
No, you'll be given any charts, figures, that kind of thing. I don't make you memorize any of that stuff.
God.
Okay, so which one of these sets is erroneous? So let's talk about when things are wrong. Okay, so let's start with A. If n is 3, L can be 0, 1, or 2. L is fine. If L is 0, M sub L has to be 0. So A is okay. So you understand my logic there?
Write it out.
Okay. If n equals 3, L can equal 0, 1, or 2. 0, okay. If L equals 0, M sub L has to equal 0.
So that's
So this is fine.
yeah. That actually
This is yes. That's okay.
Okay.
All right. I guess if you want me to write everything out.
no,
Okay.
it's fine.
So if n equals 2, L can be 0, 1, or 1. So 1 is okay. And if L equals 1, M sub L can be -1, 0, or 1. So that means that B is okay. So
D.
yeah. So C, if n equals 1, L has to be 0. If L is 0, M sub L has to be 0. There's only one choice for this one. Yeah, so that one's fine. And D, if n equals 4, L can be 0, 1, 2, or 3. If L is 1, if L equals 1, M sub L can be -1, 0, or 1. So cannot be 2, therefore that's the one that's wrong. Make sense? So with this in mind, which Which set of quantum numbers is erroneous?
The last one.
Yeah, it is D, because if n is 4, L can be 0, 1, 2, or 3, which is fine, but if L equals 1, M sub L can be -1, 0, or 1. So just so you know, it's not always L. You could have like n equals 2, L equals 4, M sub L is equal to -1. So you could have this, for instance, and this is wrong because the L is wrong. So just be aware that it's not always it's that order, but the order goes n bounds L and L bounds M sub L. Is the way that I'm trying to get you to do the logic. Make sense? Okay. All right, let's change topics and say that. Do you guys have a favorite TV show?
100.
I like Blacklist.
Blacklist. Okay.
Black Saints.
Say we have a Blacklist party, and in front of the TV
It's Victoria.
there is a lazy boy, and behind the TV there's a big comfy couch, and then behind that there are some chairs. And I guess even before that,
Why would you put a recliner in front of the couch? And block views.
because it's my party and I do what I want. So even before that, let's say I want you guys to do the same thing for 8 hours. You have to pick an activity that you're going to do for 8 hours straight.
Did that last night.
What are you going to choose? Anyone going to choose jumping jacks?
No.
Anyone going to choose sprinting up and down stairs?
I would do gas.
8 hours straight? No, you're going to pick things like sitting down or sleeping or reading. Yeah, there you go. Reclining. You probably, when you were reading, you weren't like sprinting on a treadmill, right? You were
No.
you were sitting
I was
or lying.
like this.
There you go. Yes, yes, you were in a relaxed pose. So
All night.
electrons. You read that? You didn't go to sleep.
No. It's exam week.
Okay. All right. So electrons are like people. They like to be low energy. And if you're a person and you're the first of the party, where are you going to sit?
In the front.
In the
Yeah,
front,
we're
in the
gonna
lazy
watch my
boy.
TV.
Right? Sit in the front of the lazy boy. And then as the party goes on, people will start to occupy the couch and the chair, right? So what happens though when this person here, the lazy boy, gets up to go to the bathroom?
One of your feet leaves your seat.
Yep, someone's gonna go and snag that seat, right? And when that person sits down, he or she's like, I'm relaxed. So instead of a TV and a blacklist party, say that instead we have the atoms positive nucleus, and then we have discrete energy levels, and we have electrons populating the energy levels. So what happens? Well, so you get an electron here, and this is in the closest level to the nucleus, so this is the lowest energy. This is like the lazy boy. And you can excite it. Excited means higher energy, like, I'm excited! I'm higher in energy, right? You are excited, and which means you raise in energy. And then when you sit back down, you relax. And when you relax, like, you relax down. So when these electrons, when they relax down to the different states, they can emit. So this one is going to, this is going to emit, so a blue photon, and this one going down here is going to emit a red photon. And just because it's saying red's lower energy because it goes from a lower state. So this is what this is saying: excitation, relaxation. So I'm making the analogy to like a seat at a party. So when the electrons go down in energy, they when they relax, they release energy in the form of light. And here it is for the hydrogen atom. So these are old terms, but having things go down to the n equals 1 level, that's known as the Lyman series. And down to the n equals 2 level, this is the Balmer series. We can't see the Lyman series, we can see the Balmer series. But we know the energy level of each of these. So the delta E is by this equation. Delta E is minus the Rydberg constant times the final principal number minus the initial principal number, both of them squared. So that comes from directly this equation that we showed before. This one, it's this one right here, the energy of the N. It's just final minus initial. So final minus initial, and you get this equation here. Oh, which one? Sorry, this one, that one there. That's just final minus initial. I already mentioned that's called the Rydberg constant. And where we're at right now, that is also where I ended last class, and about 5 minutes early too, actually 6 minutes early. So I still have the problem session ready. So you guys want to go to the problem session?
Yeah. You think with that session?
I'm tired. I've been here since 10:30.
I've been here since 9 and I'm sick.
Well, let's just compare whose lives are worse. 'Cause I guarantee you I'll win. I don't know.
That is true. I am married to a wonderful woman, so that is
Lucky you. I'm married to nobody.
I guess I
No,
usually don't
I'm
talk
just
about
kidding.
my wife so
You
much in
should be
class,
mine.
so you guys keep on bringing her up, so it's your fault. But okay, well I'm done. Anybody have any questions about anything? So okay,
Is this stuff gonna be on the test next week?
It's 2 weeks
it's
from
not
now.
okay.
Yes.
It's not next week. It's the
Now
week
they'll
after
start.
next. And what are fair game for the next test are things like which quantum numbers are erroneous, and the de Broglie wavelength, and the energy per photon stuff, number of photons. That's fair game. And
Are we gonna be? Can we get can we make a cheat sheet with all the formulas?
I'll give you all the formulas. But I'm gonna make you memorize the periodic table.
We just memorize the
What?
first three.
I'm joking. I'm joking.
Like, if you can memorize the periodic table, then yeah.
Can we just cut off the bottom half?
What?
That extra table on the bottom and come off to above.
No, you guys. I try not to make you memorize really anything at all, and I try to also let you. If you get confused about something, you can ask a question for clarification. So, and you can do it during the final too, by the way. It's not like it's. Okay, you guys are free to go. And I will go over to the Astro Lab for the problem session. So then-
Wanna hear my Heisenberg joke?
Sure. Let me turn this off. Is it dirty?
No,